chapter, I really wanted to emphasize the similarities between 1D motion that we studied back in September and the rotational motion that we're learning about here. When we studied 1D motion, we said that you could imagine there is a particle and that particle is constrained to exist somewhere on a number line. So let's say there's a particle right here. We said the particle must be somewhere on the number line. So if you want to know where the particle is located, you only need one piece of information. You just need to know what number on the number line is that particle located at. We called that the particle's position, and we labeled it with the symbol X. Now maybe the particle is just stationary, it's not moving at all. Okay, then we know where it is. But maybe the particle is moving around. If the particle is moving around on the number line, then that would be like saying x is changing. And we define velocity as the rate of change of x with respect to time. So we said velocity is delta x over delta t. Now maybe the particle is also speeding up or slowing down or doing something else. In that case, the velocity is not going to be constant. The velocity might be changing. And we called that an acceleration. So we said acceleration is the rate of change of velocity with respect to time. And from these definitions and ideas, we came up with relationships between initial and final position, initial and final velocity, and those were the equations of 1D motion that we worked with extensively in the beginning of this semester. Well, let's now imagine that this number line is a piece of string, so we could fold it and move it around and change its shape. We are still going to require that this particle must lie on the number line. But I could imagine that I pick up the number line because it's a piece of string. I could change its shape. The particle might be here. And I'm going to wrap this number line into a circle. So we will wrap the number line into a circle, have it meet itself, and the number line is still going to have its tick marks just like before. And the particle might be over here right now. Now, instead of thinking about describing the location of this particle with the number on the number line, I could imagine describing the location of the particle with an angle. I will choose to have this circle at the center of a coordinate system. In other words, the origin is going to be right in the center of the circle. Here is my x and my y axes. And right now, at this instant, the particle's right here. So I could draw a line and I could say this angle theta is all the information I need to describe the location of the particle. At some time later, the particle might have moved over here. Well then, my angle would have changed. So I could completely describe the position of the particle with one piece of information, and that piece of information is the angle. Remember, we are still requiring the particle to lie on the number line. In this case, we have twisted the number line into a circular shape. That's like saying I am requiring the particle to be somewhere in this circle. Now, if the particle is moving around in one way or the other, then the particle will be changing its position on the circle. That's like saying the particle's angle is going to be changing. We'll call that angular velocity. Angular velocity is the rate of change of angle with respect to time, and angular velocity is designated by a lowercase Greek letter omega. It looks like a lowercase w, but it's a Greek letter, and that is delta theta over delta t. Now also, if the particle is moving at a nice constant rate, then the rate of change of angle with respect to time will be constant, omega will not be changing. But maybe the particle is moving around and speeding up faster and faster. If that's the case, then I could say omega is increasing or decreasing, depending if the particle is speeding up or slowing down. And I could call that an angular acceleration. Angular acceleration is designated with a lowercase Greek letter alpha. This is not the letter A. And alpha is the rate of change of omega with respect to time. Using a technique, very similar to how we derived the equations of motion for 1D motion. We could come up with equations of motion relating the initial and final angle, initial and final angular velocity when we assume constant acceleration. And those equations are theta final equals theta initial plus omega initial t plus 1/2 alpha t squared. We have omega final equals omega initial plus alpha t, and we have omega squared final equals omega initial squared plus 2 alpha delta theta. If you compare these three equations to the three equations we worked with when we considered 1D motion, theta is basically taking the place of x, omega is taking the place of v, and alpha is taking the place of a. In this first example problem, we are told that there is a diver that steps off a 10-meter high diving board, and as the diver descends towards the water, the diver is spinning. On the way down from the diving board to the water, the diver goes through 2.5 revolutions. So 2.5 revolutions on the way down to the water. If the diver has an initial velocity of 0 and 0 initial angular acceleration, what is the diver's angular velocity as he's falling towards the water? So for this picture, you could kind of imagine that the diver is rolling off the diving board and then he continues to spin around and around as he descends to the water below. 2.5 revolutions is going around a circle 2.5 times. We like to work in radians in this chapter, so 2.5 revolutions is an angle. I'm going to convert this angle to radians. So if I think about the relationship between revolutions and radians, 1 revolution is once around a circle, 2 pi radians is once around the circle. So I could multiply 2.5 revolutions times 2 pi radians per 1 revolution. And when I cancel the units of revolutions, I get the diver has spun through an angle of 5 pi radians. We just did a unit conversion. We did not really do any physics yet in this problem. If I wanted to, I could get a decimal number by multiplying 5 times pi, but it's just easier to write 5 pi, so I'm just going to leave it like this until the very end of the problem. Now let's ask the question. This is the angle that the diver spins through. At the top of the problem, at the very beginning when he steps off the diving board, he has not spun yet. So we could say his initial angle is going to be 0. So I'll write theta naught is 0. And by the time he gets to the water below, he has spun through this much of an angle. So I could say he goes from not having spun around yet at the top of the diving board to having gone through an angle of 5 pi when he gets to the water below. Let us now ask the question, how long does he spend in the air? How long does it take him to fall the 10 meters? To answer that question, we are going to take an idea from chapter 2. We're told the diver has 0 initial velocity. We know how high he is above the water initially. So we could use an equation of motion from chapter 2, 1D motion, to answer that. I could say y final equals y initial plus v naught yt plus 1/2 ayt squared. And when I plug numbers in, y final is 0, the level of the water. We'll say final height is 0. That implies the initial height will be 10. We are told his initial velocity is 0, so multiply that by 0. And then plus 1/2 times negative 9.8 acceleration due to gravity t squared. And when I put these numbers into a calculator, I find that he spends an amount of time of 1.43 seconds in the air. So t equals 1.43 seconds. Now the question is asking, what is his angular velocity? To answer this question, we are going to use one of the equations for rotational motion that we introduced in this chapter. Specifically, we are going to use theta final equals theta initial plus omega initial t plus 1/2 alpha t squared. Let's look at this equation. Let's see what we have. We were told in the problem he has 0 angular acceleration. That means alpha is 0. So I could say this term is 0. This was given. We also know how long he spends in the air. That will be t. We found his time in the air is 1.43 seconds. That is essentially just asking how long does it take to fall from a height of 10 meters to the water below. Also in this problem, we concluded that he has spun through a total angle of 5 pi radians. In much the same way, when we work with x final equals x initial plus v naught xt plus 1/2 axt squared, we said you can set up the origin of your coordinate system anywhere you want. So in many problems, it was convenient to say, we'll set the initial position to be 0, and then whatever the final position is, however far the object travels, that will be x final. By a very similar style of reasoning, we chose that at the beginning of the problem, he did not spin at all. So we will say at this moment, he has not yet rotated through any angle. I chose to set his initial angle to 0. We then were told between the initial moment and the final moment, he made 2.5 revolutions. Between the initial moment and the final moment, he made a rotation of 5 pi radians. By setting his initial angle to 0, that means his final angle must be 5 pi radians. So I know what his initial and final angle are. I know what the time in the air that he spends is. The only term left that is undetermined is his initial angular velocity. So I could write theta final is equal to 5 pi, theta initial is 0, omega initial is an unknown that we're solving for, and the time he spends in the air is 1.43 seconds. If I then put this number into a calculator, I find that his initial angular velocity is going to be 10.98 radians per second. Omega naught is 10.98 radians per second. At this point, we are done with this problem. An analogous problem that we might have encountered in Chapter 2 is, suppose we were told a car travels 1 mile in 52 seconds. If the car is not accelerating, what is the velocity of the car? To draw that problem out, we would say, okay, the car begins here. We'll set the initial position of the car to be 0, and the car travels 1 mile. So the car travels 1 mile. So here is x final, which is 1 mile. We could convert miles to meters, and we would get 1609 meters for the distance the car travels. We have our initial and our final position of the car. We were told the car does not accelerate, so that would be like saying a is equal to 0. And we know the car travels for 52 seconds, so t equals 52 seconds. When I am given this information, I could say x final equals x initial plus v initial xt plus 1/2 axt squared. I could plug in these terms. Because the car is not accelerating, its initial velocity will be constant. It will have the same velocity throughout its travel, and I could then solve for the velocity of the car. This problem from Chapter 2 material is the analog to what we just solved here. We are told that there is an insect sitting on the edge of a record, and that record spins through a rotation of 3 pi over 4 radians. We're asked how far does the insect travel if the record has a radius of 5 centimeters, and how far does the insect travel if the record has a radius of 8 centimeters. So here's a picture of the record, and I chose to put the insect right here on the record. The initial starting location of the insect does not matter ultimately. You could choose to put the insect anywhere you want on the record. Is there a reason why I chose to have the insect be right there? Well, kinda. If I imagine that there is an XY coordinate system with the origin right at the center of the record, then I have the insect starting along the x-axis at an initial angle of 0. I do not need to work with this convention, but drawing my coordinate system like this makes this problem a little more familiar to me, and it's just a little easier for me to think about. So we could say the insect initially begins right here, and the record spins through an angle of 3 pi over 4 radians. So where will the insect end up? Well, one complete revolution of the record is 2 pi radians. So 2 pi radians would be going around once. If 2 pi radians is going around once, then pi radians would be making half of a revolution. And therefore, 3 pi over 4 radians would be 3/4 of this. So 3 pi over 4 radians would be the insect ending somewhere around here. So I could say in the record making this rotation, the insect has moved through an angle of 3 pi over 4 radians. Theta equals 3 pi over 4. And we are asked to find through what distance does the insect travel. So that is asking what is the length of this arc. To answer this question, we could use the relationship between arc length and radius of a circle. We have the arc length of a circle is given by r times theta. We will say that r, the radius of the record, is 0.05 meters. We convert centimeters to meters. And therefore, I could say the length of the path that the insect travels is given by 0.05 meter times 3 pi over 4 radians. And I find that is equal to 0.0118 meter, which is equal to 11.8 centimeters, depending on how I want to convert it. Similarly, if I consider a larger record of radius 8 centimeters, I could say the arc length, that is the insect's path, would be given by 0.08 meters times 3 pi over 4 radians, which gives me a distance traveled of 0.188 meter, which is 18.8 centimeters. In the third example problem, we are told that there is a dentist drill, and when the dentist turns on the drill goes from not spinning at all to spinning at a rate of 25,100 revolutions per minute. So let's think about what's given in this problem. Initially, the drill is not spinning at all. That would suggest that the initial angular velocity of the drill is going to be 0. So I could write omega naught is 0. Now, after 3.2 seconds, the drill is spinning really, really fast. What does that really mean? Well, if you imagine there were a mark on one side of the drill, you could ask through what angle is that mark moving every second? That would be like asking what is the final angular velocity of the drill? How rapidly is it spinning? After 3.2 seconds, the drill is spinning this rapidly. It's moving around over 25,000 times every minute. So I could write the final angular velocity of the drill is going to be 25,100 revolutions per minute. When we work with rotational motion problems, we want to work with our angles in radians and our time measured in seconds. So revolutions per minute, I will convert to radians per second. I could say that there are 2 pi radians in 1 revolution. So I will put revolutions downstairs since revolutions is upstairs here. And there are 60 seconds in 1 minute. I will put 1 minute upstairs because minute is downstairs here over 60 seconds. And when I do this conversion, revolutions and revolutions will cancel, minutes and minutes will cancel, and I find that the final angular velocity of the drill is 2,628 radians per second. Let's think about what we're given in this problem. We are given an initial angular velocity, we're given a final angular velocity, we're given the amount of time between the initial and final angular velocity, and we are asked in part A to find the angular acceleration. Essentially, part A asks us to find what is alpha. We could look at the three equations for rotational motion we have considered so far. And if we look at them, one of them has all three of these terms plus alpha in it. That equation would be omega final equals omega initial plus alpha t. So I could just plug these numbers in. This problem of part A is analogous to if an object is initially at rest and then moving at some really fast speed in some amount of time, what was its acceleration? So here we could say 2628 is equal to omega initial plus alpha times the time of 3.2. And when I put these numbers in a calculator, I get the angular acceleration is going to be 821 radians per second squared. In part B of this problem, we are asked through what angle does the drill spin? So you can imagine there might be a notch or a scratch on one side of the drill, and as the drill spins, that scratch is going to be spinning around. We're asked through what angle does that scratch spin? The 1D motion analog to part B of this problem would be something to the effect of if an object is initially at rest and has a given final velocity and it went through constant acceleration in some amount of time, we solve for the acceleration of the object. How far did it travel while it was accelerating in that amount of time? So for this problem, I could say theta final is equal to theta initial plus omega initial t plus 1/2 times alpha t squared. In the same way that when we work with 1D motion, we can choose the initial position of an object to be at the origin at x initial equals 0, I could choose the initial angle of the dentist drill to be 0. And then the final angle will be the total angle through which the drill has spun. So I'm going to make that choice. I would then say the final angle of the dentist drill is equal to 0 plus omega initial, we set as 0. It's initially not spinning. 3.2 seconds for time, plus 1/2 times the angular acceleration that we found, 821 times 3.2 squared. And if I solve this in a calculator, I find that the angle that the dentist drill has spun is 4,200 radians. You might notice that this angle we found is much larger than 2 pi radians. 2 pi is about 6.28 and 4,200 is much larger than 6.28. So how should we interpret this result? Well, if the drill spins through one complete revolution, then I would say the drill spun through an angle of 2 pi radians. If the drill spins through 2 complete revolutions, then I would say the drill spins through 2 times 2 pi radians, or 4 pi radians. In this case, the drill spun through 4,200 radians. If I divide 4,200 by 2 pi, I get about 670. So I interpret this result to mean that the drill spun around many times, almost 670 complete revolutions, while it was speeding up to its final angular velocity.